So you actually would get some hydroxide being produced here. So you get hydroxides being produced, and you would get two of them being produced every time you react to water, right? But on the other side, you have water being oxidized, and that's producing your oxygen gas, but it's also producing two H pluses. So really, every time water undergoes reduction and oxidation, there is basically an equal amount of hydroxide and hydronium being produced. So the overall pH should not change in this situation. So hope that kind of makes sense there. Next question you might be asked is, how much voltage would you actually need to make this happen? Because this, remember, this reaction is non-spontaneous. It's not going to happen unless you give it some energy, which is what the battery is trying to do. So basically, we could work out the E naught of the cell. And now what we have to be careful about here is we're using, well, there's a couple things to be careful about, I guess. One is we're using these two voltages, because those are the two reactions that are doing something. And we have to know which one to flip here. Remember, one of them always gets flipped. So if we take the reaction that's for reduction, which is actually the lower one, then we don't change that number. That's actually negative 4,1. But this reaction, Beaker is very concerned. That reaction is oxidation. So we actually have to flip that to negative 0.82. So we're going to minus 0.82 then. So we're going to take negative 4,1, and we are going to minus 0.82. And so we get negative 1.23. Okay, so that is actually the E naught of the cell. Now notice it's negative, which means it cannot happen on its own. So the battery had better be 1.23 volts or more. So you're going to have a battery with probably more than 1.23 volts to, or at least a minimum of 1.23 volts to drive this reaction. So if you had a 1 volt battery, nothing would happen. It's not powerful to make this occur. So that's tricky. Let's try one more that type there. Okay, so I'm going to take a look at this one here, nickel iodide. Okay, and let's see what we get here. So I'm going to, you guys can pause the video if you want. I'm just going to launch into the question. So reduction, oxidation. Well, what do we have present? Well, we've got nickel ions, and we've got iodide ions, and we also have water now. So we've got to always remember water because it's molar. That doesn't mean molten. That means molar, moles per liter. So what can we reduce? Well, we just saw that nickel ions are positive, so we can definitely reduce the nickel. And we can definitely reduce the water too, remember? So let's see if we can place that first. So nickel is at negative 2.6. And the water reaction is negative 4.1. It's actually even lower down. So there's the water. And once again, if you look at your data table, you'll be able to find these things. I think just watching the video and not having a data table in front of you is not terribly helpful for your learning right now. And then, of course, the iodide, that is actually on the other side of the table. And that's at 0.54. And then the water reaction is above that one, and it's the same as the one above, so that's 0.82. Okay, so we do have a step-up reaction. There's multiple step-up reactions here. And really what the battery is trying to do is pick the reaction that has or requires the smallest voltage possible. So really the one that's further up on this side is the more likely one to get reduced, and the one on this side is the more likely one to get oxidized. So you're really looking for the smallest step up here, the smallest possible voltage required. So the nickel ions are higher up than the water, so they are going to undergo reduction, and then the iodide ion is lower than the water, so it's going to undergo oxidation. So nickel should wind up producing nickel solid. Of course, you need 2 electrons for that, and then the iodide will undergo oxidation to produce I2, requires 2 electrons, and of course 2 of the iodides. Okay, so where do the electrons flow and how do we determine the anode and cathode? Well, electrons flow out of the negative end, so electrons are flowing that way, which means that's the anode. This is the cathode. And this is usually why I make the electrodes out of different metals, so that you could say, oh yeah, the carbon electrode, that's the anode. And you're like, which carbon? There's two carbons here. So generally I try to create two different metals here, but this one I didn't. Okay, so nickel is undergoing reduction and aux cared. So reduction happens at the cathode. So the nickel is going to go towards the cathode, and this is water, so is in water, sorry. So the temperature is at such that you actually would see some kind of layer plating on the surface here, and that would be nickel. Okay, so you get nickel solid forming. And in the other beaker, the iodide, it's moving towards the anode. It's undergoing it's undergoing oxidation, and so we got it getting I2 forming, and that I2 would be a solid here. So I2 would form. So you might actually see a layer forming on here. So here's a reaction where the water doesn't react at all, whereas the reaction above, the water was the only chemical that reacted. Okay, so I'm gonna do one more example here, and then we'll call this video quits. Whoa. Okay, so let's take a look at, go back to being two different metals, platinum and carbon, or two different electrodes, I should say. And we have a DC power source. And let's make this the negative end. We'll make this the positive end of the battery, okay? And let's put a solution in here, so we'll fill it up. And let's make this, the little trick is the last tricky question of the day. 1 molar, let's go sodium chloride, okay? So table salt, you take some table salt home and you stick a bunch of electrodes in, attach it to your parents' car battery, and then you run away, okay? So you run really far away. Okay, in fact, if you did this in the ocean, if you took your car battery and dropped it in the ocean at your feet, this might actually happen. So let's take a look and see how risky this is. Okay, so let's take a look at reduction and oxidation. Okay, so what's going on here? What do we have in the solution? Let's choose a nice color for some ions here. Let's choose some bright colored sodium, some chloride ion, and then we'll make water, blue. H2O. There we go. Okay, so we know sodium ions can definitely get reduced. So they're definitely on this side. And they're really far down though, so negative 271. And then we know water, we've done this a few times now, we have water up here at negative 0.41. And then we have water, water blue. We have water over here, and that's 0.82. And then we have the chlorides up here, and the chlorides are at positive 136. Now you need to have a data table to understand what I'm about to say next. Otherwise you're gonna be like, what? Okay, here we go. So furthest thing up on this side is water. So water. And then the furthest thing down on the other side is water. So this looks right now like the first question we did here with the one the beaker is looking at here. So we go down here, and now we got to be very, 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 very careful. Okay, so water does get reduced. That is true. Water does get reduced here, okay? However, water does not get oxidized, okay? Even though it is lower down on the right-hand side. And this has to do with what's referred to as the overpotential effect, okay? Now, you don't have to understand what it exactly that means. You have to understand this, though, and you can see it on the table, so it's not like I'm trying to trick you. It's actually right on the table. You will see a dotted line coming out, going up, and across like this, okay? And then just like that, and it says overpotential effect. And once again, you don't need to know what the overpotential effect is or how it works, but you have to understand that water is technically above chloride because of the overpotential effect. So although it's lower on the table when you look at it, it's actually experimentally higher than chloride, which means all the chemicals under chloride, including chloride, will get oxidized before the water will. So it turns out in this reaction, the chlorides actually get oxidized here. So we get that going that way, and we get this going that way, okay? Now, once again, you might be saying, well, why? And once again, you don't need to know why, but experimentally, if you react this, the chlorides always react before the water does. Same is true for bromide, if you look on the table there, or manganese ions in water. There's a lot of different equations we can take a look at that actually wind up getting oxidized before the water does. Okay, so what forms then? What forms? Well, just like the question above, the water will produce 2 hydrogens, and also, I'm sorry, we'll produce hydrogen gas. Sorry, my bad. Looking at the wrong reaction there. It'll produce hydrogen gas, and it will also produce hydroxides. So that's gonna change the pH. But another question I didn't, because there was the same number of hydrogens being produced. So where is that going to happen? Well, we know the electrons flow from the negative end out. So they're flowing outwards. So they're kind of flowing in that direction, which makes this the cathode on this side and makes the carbon the anode here. So the platinum is the cathode, the carbon is the anode, and the cathode is where reduction occurs. So the water is going to move towards the platinum. It's going to undergo reduction, and you're going to see bubbles forming. And what gas are those bubbles? Well, those would be hydrogen gas. So very dangerous. And you would also get hydroxide ions being produced. Okay? Now, at the anode, that's the oxidation. Remember we said the chloride overpotentialed the water. So the water overpotentialed the chloride. So the chloride ions, they undergo oxidation. They turn into chlorine gas, Cl2, and 2 electrons. You need 2 of those. So the chloride would move towards the carbon electrode. You would see bubbles forming. And those bubbles would be chlorine gas. So this battery, this setup, this electrolysis, this would be one heck of a way to go out, right? Like you've got chlorine gas, which would be extremely poisonous. And if you were smoking a cigarette at the time, that'd be pretty cool, actually. So as you fell to the water, the hydrogen gas would ignite and create a giant fireball. Wow, so sad. Anyways, here we go. So don't do this. Don't ever do this, please. So don't go to the ocean and throw car batteries into the ocean. I'm sure it's not good for many, many things. Okay, so what voltage is required here? So the E naught of the cell, so the E naught of this cell, we got to switch the oxidation reaction. So the oxidation reaction is this one, right? So that's going to become negative 0.82. We keep the reduction reaction at negative 4,1. And now what we do is we add these 2 numbers, or we subtract them, I guess you can say that way. So 0.82, not times, 0.82, and then 0.41, and that's going to give us negative 1.23 volts, right? So negative 1.23 volts. And that's going to be the E naught of our cell here. And I'm going to stop the video there because that actually concludes our lesson for today. So I'll post some questions online, and we'll see where we